When we look at the energy changes that happens in a chemical reaction, you must make very sure that when you're talking about energy, you know whether you're talking about the surroundings or you're talking about the system. The system is basically the chemicals there inside. Now, when we look at exo and endo, you've done this in previous grade where you just say, if it's an exothermic reaction and I touch it, I'm going to feel that the container is hot. So you can see that the thermometer there is red, so the container is hot. When it's an endothermic reaction and I touch the container, I know that it's going to be cold. So most of you have done that in lower grades. But now why is the container hot and why is the container cold? And now we have to look at what actually goes on inside. So any chemical reaction has got to do with bonds that has to be broken and bonds that has to be formed. So if I look at this very simple reaction here, it's just oxygen and hydrogen reacting with each other, and we'll know that that's going to form water for us. Then you can see that we've got hydrogen, H2, and we've got oxygen, O2. And now, before they can form this, all these bonds must be broken. So you can almost say you have to put something in between and tear them apart. So to break these bonds, I have to add in energy. So whenever I break a bond, I have to put energy into the system. Then it forms a mushmash of loose, you can almost say, atoms here in the middle. But anything in nature wants to be at as low as possible energy. So what's going to happen is when I'm forming the new bonds, energy is always going to be given off, because something will not bond if they can't get a lower energy by actually bonding from this state, is what I mean. So then to form these bonds, energy will always be given out because they now want to go to a lower energy state. Now it just depends on how much energy I put in and how much energy I get out, whether it's going to be an exothermic or an endothermic reaction. So let's use simple values, and we say to break these bonds, these are not true values, to break these bonds, I have to put in an energy of 100 joules. And you will see these are measured in joules per mole. But actual calculations for bond breaking and bond forming are not needed in your exam, but you need to know the basics of what goes on here. So if I put 100 joules of energy in to break these bonds, and when these bonds are forming, I give off 150 joules. Now you just have to think for yourself. I've taken in 100 joules, so these chemicals took in 100 joules from the environment. Then it gives out 150 joules to the environment. So what did the environment end up with? The environment ended up with more energy than what it originally had. So that is when you're going to touch this container, you're going to feel that more energy than what it had before. So you're going to feel that it's hot. So this is going to be an exothermic reaction. But now you need to think about these chemicals. The chemicals are taking in 100 joules and they're giving out 150 joules. So did the chemicals end up with a lack of energy or more energy? And now if they only took in 100 and they give out 150, the chemicals end up with minus 50 joules of energy. And this is the energy that we are looking at when we say delta H. So it's the potential energy of the chemicals, not the environment. We're interested in the chemicals. So if the chemicals themselves have lost energy to the environment, then that is our delta H value. And if it's negative, then we're always going to have an exothermic reaction, because if the chemicals lost energy, the environment gained that energy, and therefore when you touch it, it's going to be hot. I'm going to do the same thing again. This reaction, specific reaction, will be an exothermic reaction. But just for the sake of the example, let's just say somewhere in a different universe, this bond breaking here, still it will be energy in always, because bond breaking always will require energy. So you need energy for bond breaking. So let's say we take in the 100 joules still to break those bonds, and we end up with our mush of loose atoms. But now to form these new ones, I only give out 50 joules of energy. Again, think about the environment and think about the chemicals. So if I think about the environment gave 100 joules to break these bonds. So that's what went in. So, and it only got out 50 joules from the chemicals. So now I've given in 100, I'm only getting out 50. So that means the surroundings, the environment, lost 50 joules of energy. So when I touch that beaker, it has lost energy. So now it's going to feel cold. Remember, you're not sticking your finger into the middle of the chemicals. You're touching the surroundings. So that has lost energy and therefore it feels cold. But now if we look at the chemicals, because remember, anything in nature is always balanced. So there's going to be a conservation of energy still. So the energy that the environment lost by cooling, the chemicals, the potential energy inside the chemicals is now going to increase. So the chemicals took in 100 joules and they only gave out 50 joules. So in total, the chemicals inside has gained 50 joules of energy. So they've gained plus 50 joules of energy. Like I said, joules per mole normally, but they've gained 50 joules, and that means that they've got a higher energy, and that will be an endothermic reaction. So when this delta H then is positive, then you know it's an exothermic reaction because the chemicals gained energy, but it gained it from the environment, so the environment will cool down. Now we need to just look at the terminology. So that delta H is called the heat of the reaction, and that is the net change then in the energy of the system. So that, and when they say system, it's the chemicals they're talking about. So the system, if the system gained energy, delta H is going to be positive, and my container is going to be cold. When the system lost energy, delta H is going to be negative, and my container will feel hot. Now, where do we need that now? Just throw that little picture away as well. So now we're going to look at what actually happens here. So remember, you'll see these graphs are exactly what we're heading towards, and you've seen them before. I have a little dot there that irritates me. Here we go. So if I look at so now we're going to look at what happens here. So this is just methane reaction with oxygen, so a normal combustion reaction in organic chemistry. And there's this energy that you see here, or potential energy. Remember, it's the energy inside the chemicals, not the system. So you're sitting with this as your reactant. Also use the right words. The reactant is what we start with. Now we have to break the bonds. Now remember, to break the bonds, I have to put in this much energy. Then I end up with this mush of chemicals here. No one knows what it looks like. It's obviously not going to be arranged like that. No one can isolate that because it's very unstable. It's just a transition state. And in this state, it doesn't want to stay. It wants to form lower energy. So it always drops down from there. Now it just depends, does it drop more than what it gained? So in our first example, we had 100 joules in. I know it's not the same for this reaction, it's just to make it simple. And we had 150 joules out. So now you can see the environment ended up with more energy. But when you go and do your delta H calculation, it's always from where your products are now, minus where you started. So you can see here, you're going to have this value here, which could be anything on your graph, minus this value here, which is much bigger, and therefore you're going to end up with a negative answer. So the graph values also make sense. If I don't end up below there, and I'm going to do these graphs for you just now again. If I don't end up below where I started, but my products are here and my reactants are here, that means I added in this much energy, but I only give out that much energy. Now that extra energy is sitting inside my chemicals. So my chemicals stole energy from my environment, and that means it's going to be a high value minus a low value, and my delta H will be positive, as we said before. So again, the maths makes sense. So just always think, did I give in more energy or did I take out more energy? And when you think about that, you're thinking about the chemicals. So this is very important. Your delta H value is going to be bigger than 0 for an endothermic reaction and smaller than 0 for an exothermic reaction. And this is important for rates and equilibrium. All right, I think we've covered all those points. Just remember, by saying that bond breaking needs energy, I am saying that it's endothermic, because when energy is taken in, it is endothermic. And bond formation is exothermic. It's always going to release energy. And we said that. We take energy in to get the mush of atoms, and then we have to give energy out to form the new. It just depends on how much I give out. If I give out more than what I took in, then it's exothermic. If I give out less than what I took in, then it is endothermic. Now that is why if we define endothermic reaction, it transforms thermal energy into chemical energy. So the energy that the chemicals had is now inside for endothermic is now inside the chemicals, so the system cools down. And if we look at exothermic, that means that the energy is, there it is, the chemical energy is now thermal energy. So the chemicals here lost energy to the environment, and therefore it's feeling hot. All right, so now the graphs you get is not going to look like this with nice pictures, sadly. You are going to get these graphs that just look like this. Let me just move it. And now these graphs are super important because they ask them all the time. So when you see this is called an energy profile, potential energy profile. So on your y-axis, you will always label potential energy. This is not time, it's reaction progress, because you know that when that hydrogen-oxygen balloons that we've exploded so many times happens, it happens in a split second. So you can't put that nicely on a graph like this. And some reactions takes very long to happen. So this is just the reaction progress, or it's not time. And that's why I don't want you to really use this one, because it's not time. This is the one that you will get. Now the mush of atoms at the top here is called the activated complex. So you need to know that definition. The activated complex is the mush of atoms that I said, the loose atoms that you reach here. But to reach that, you need to add activation energy. So the energy that we add when we break these bonds apart is called the activation energy. And then we give out energy, and the difference between the reactants and the products. If the total difference was energy released, we know it's exothermic now. And if the total difference is energy gained, then we know it's endothermic now. So I have these nice ones as well. Just remember, it's not time. So if it's an endothermic reaction, again, the bonds were broken. All this energy was given in, and that's called the activation energy. It's abbreviated as EA. I get this transition state that we call the activated complex at the top, and then I give out energy. In this case, I gave out less energy to the environment than what I took up into the chemicals. So therefore, the container is going to feel cold, and my new bonds are going to have less energy than more energy than what I had before. So it stole energy from the environment, and the environment is cold. And that means my delta H is positive, because the chemicals now have more energy. So that's for endothermic again, and then for exothermic, just to make sure you get it. Again, we have reactants. The bonds are broken by adding energy. activation energy, I reach this mush of chemicals at the top, which is called the activated complex. I then always will give off energy, and in this case, I'm giving off more energy than what I had. So this difference is what goes to the surroundings. So my delta H is my products minus my reactants again. Always final minus initial is my delta H, and this time it's negative. If it's negative, the chemicals have less energy, so that energy lands in the surroundings, and therefore my container will feel hot. Now for these ones, and it's not really mentioned in the SAGs here, but I just want to quickly mention the Maxwell-Boltzmann graphs as well here. So for a Maxwell-Boltzmann graph, you will see that they are talking about the number of particles with a certain amount of kinetic energy. Now, the kinetic energy must be higher than the activation energy for a reaction to start. So you'll see the definition for activation energy is the minimum energy. So it's this energy here, the minimum energy that I need for a chemical reaction to start, or to the minimum energy I need to reach that activated complex at the top. So now, what has that got to do with reactions? Only when it can reach that point, and when there's a successful or an effective collision, is when a new bond can now form. Now, there's two things, and if you remember in class, I used the clapping example. So if you clap your two hands together, it's the correct orientation, but you guys can still not hear me, and I'm doing it right now. I also need high enough energy. So there's two things, and if I clap with very high energy, but my hands are not orientated next to each other, then it's not the correct orientation. So these two things are very important. To have an effective collision, I have to have the correct orientation. And what do we mean by sufficient energy? Sufficient energy means I need this energy here. So I need energy higher than the activation energy, or equal to the higher activation energy for a reaction to take place. Now, a Maxwell-Boltzmann curve almost feels as if it should be the other way around, because it says number of particles here, and on the x-axis you've got the kinetic energy. So when you look at these particles here, they do not, so the area under the graph is basically the proportion of the particles that we have. So now all these particles do not have enough energy to overcome the activation energy, or not higher energy than the activation energy. The kinetic energy, the activation energy here, is equal to the activation energy, and anything higher than that would mean I do have an effective collision now. So only this proportion of the particles can react. And this becomes important later when we look at the factors that affects the rate of a reaction. Now let's look at those factors that affect the rate of the reaction. But before we do that, we have to look at how we measure these reactions, because there's a few different ways, and they love putting different ways in your papers, and you need to be able to do all of them. Now, I've thrown a few pictures on top of each other here, and I'm just going to go through them quickly. There are a few that they often ask. So if you look here, electrical conductivity, that would be in the case where you're forming ions. If you're forming more and more and more ions, it will become more and more more and more conductive. If you're forming less and less ions, it will become less and less conductive. So that one I haven't really seen in a final paper. pH, you can look at when the pH reaches a certain level, or when the pH stops changing. That's specifically in acid-base reactions. You can look at the color as the color is changing. You can look at how the reaction happens. You can look at, where's this one? This one we actually did in class, and I think lots of people do this in class. You've got a cross at the bottom of the container, and then you look from the top and you stop your stopwatch when you can't see it anymore. So this is when a solid is forming. So when a solid is forming, you can measure the turbidity. There you can have a turbidity meter as well, but here we just looked at when when the cross disappeared. A lot of you did those as well. But now what has this got to do with the rate? Because remember, rate is always in a specific amount of time. So all of these things are worth nothing if you don't actually measure the time, because rate, remember in physics as well, when you say rate, it's something per unit time. So whatever you measure per unit time, but be specific when you talk about the definition. Reaction rate is defined as the change in concentration per unit time of either what you started with or what you end with. So the concentration of the reactants or the product. But you need to remember that it's per unit time, otherwise it's not rate. Now, when you get a graph and you have measured one of these things, let's say we've measured pH over time, the pH changed and changed and changed, and then it didn't change anymore. So this one went higher, so it became more basic. So what you would say then is the rate would be the change in the pH over time. So if you look at that, the change in pH over the change in time, if this is the time here, I'm hoping that you can see that this is actually the gradient of the graph. So you must be able to calculate the rate if you get given a graph by getting the gradient of the graph. So the rate of a reaction, always given by the gradient, if it is something that you've measured over time. Don't think it's always, think about your graph as well, because sometimes it's a rate graph. Okay. So just quickly here, and we're going to use this for our next bit. So this one is a one that is often given. You can look at the mass change of the system. So be careful also, sometimes it's plotted as the decrease in mass, and sometimes it's plotted as the change in mass. So the loss in mass. So in the beginning it would be 0, and then it will be going up. But again, the gradient of this graph shows you that in the beginning there was a fast rate, and you're going to be asked to use the collision theory to explain this. Now, collision theory means if two particles collide with the correct orientation and energy, there will be an effective or a successful collision. So in the beginning, there are lots of reactants. So there's lots of reactants that can collide with each other, and therefore they can have an effective collision. As products are forming, so as the gas is forming here, there's less reactants. So less successful collisions can take place, and therefore less products can form until the reaction stops. So this is not equilibrium, it's just for a one-way reaction. So this is the one way you can do it. You can also measure the gas gain. And please remember that the gas formed is exactly the same as the gas formed is the mass lost. Because the only reason why we're losing mass is because the gas is leaving the system. I don't know why my board doesn't want to work. It's doing its own little thing again. It will wake up now. All right, so now we're going to look at the different things that we can do to change the rate of this reaction. So I'm going to specifically look at this one. Now remember, you can have a syringe like we had here, but you can also collect the gas formed using the downward displacement of water. We can also measure the pressure. Remember, the pressure is we've done an experiment where we measured the pressure built up in a tube. That could also be something that you measure. Anything that you can measure that is an indication of the gas formed in a specific time would be good for a rate. Now, if we look at this, we're going to look at this reaction. So if we look at the gas formed there, and I draw a quick graph. So it's going to be the volume of gas over time. And I draw a graph. So gas is going to form, and then it's going to stop forming. So when this line levels out here is when the reaction has actually stopped, and I have formed my limiting reagent. Please remember that quantitative can be anywhere. My limiting reagent has been used up. So highlight the limiting reagent. If they give you a question like this. So that would be my graph. Now we're going to look at, well, how can I change the rate of the reaction? And you need to know the different factors that can change the rate of a reaction. So the first one, and we're just going to use this. So this is magnesium powder and acid. We have done this reaction before. So now if I want this reaction to happen faster, and now very important, let's say that our magnesium is our limiting reagent. So if my magnesium is my limiting reagent, it means that magnesium determines where I stop here. So there's always two things you need to think when you need to go and draw a new graph. You need to think, am I forming more product or the same? And am I forming it faster or slower? So faster or slower would be the gradient. Product would be your endpoint. Now let's see. The one thing that we can do is we can add a catalyst. The first thing is a catalyst. So a catalyst is defined as something that increases the rate of the reaction, but it remains unchanged at the end of the reaction. Now, a catalyst is something that gives particles the correct orientation to react. And so in a way, it gives the chemicals a path of lower activation energy. So they can easily reach that activation energy there will not be as high, so it gives it a path of lower activation energy. It doesn't affect my products or my reactants because we said it doesn't change in the reaction, but now more particles can reach this activation energy than what could reach that activation energy. So now my reaction is going to happen faster. So I'm going to have a higher slope, but as we said, it's not going to affect my product, so I'm going to still end up exactly at the same place. So that is for a catalyst. And I'm going to go through the points that you need to mention when they ask you to use the collision theory with you now. So that's if I add a catalyst. The next thing I can do is heat this all up. Now remember, if I'm heating it up, the particles are going to move faster. So they're going to collide faster and they're going to form product faster. So again, it will look like the catalyst one because there is not any, it's the same product, same reactant. So there's not going to be more product formed. And then pressure, if there are gases and you squash gases together, so if the pressure is higher, it means you're squashing them together, so they're actually moving in a smaller volume. So again, this would happen, but if you haven't changed the amount that you had, it will still look like that. So an increase in pressure would also look like that. And then you can also change the concentration. So if I change the concentration, now you must be careful. Magnesium was my limiting reagent. So if I increase the concentration of my acid, I might have more acid, but it's not my limiting reagent. So it's going to happen faster, but it's still going to end at exactly the same place. And then the last one is if I have a solid, I can increase the surface area. So instead of having a big block like this, I cut my block in half. So now this area here was exposed. Now those inside areas are also exposed. So there's more exposed particles, faster reaction. But again, it doesn't form more product. So the only time when you're going to form more product is if they say to you, you have more stuff. So you have more of my limiting reagent. So instead of 10 grams of magnesium, I'm now using 20 grams. Then it's going to be a higher product that forms. Now we are going to look at the collision theory and how the collision theory affects all these different things. Now, I'm going to use that same graph. So the first one is for a catalyst. So these questions are normally 4 marks. So you need to think, I need to get 4 marks for my answer. So 4 points. And please, you are allowed to put it in point form. So catalyst. I think I'm going to just type it so that you guys have it here. So when I have a catalyst, that's minute. Let's just make it a little bit bigger. Okay, so when I'm adding a catalyst, what am I actually doing? I am giving does a catalyst allow a path of lower activation energy? Because it has a path of lower activation energy, more particles can overcome this activation energy. So if more particles can overcome this new activation energy, there will be more effective, can't spell, collisions. If there are more effective collisions, but you can't just say collisions because it's rate. So if there are more effective collisions, doesn't really help. It has to be faster as well. So you have to say more effective collisions per unit time. And because there are more effective collisions per unit time, there will be a faster rate of the reaction. So please, you don't have to write paragraphs. Use those points. There's always 4. The catalyst allows a path of lower activation energy. More particles can overcome this activation energy, therefore more effective collisions. Now, if we look at the 2 graphs, so if you now had to draw the graph, remember if that was our original graph there, for a catalyst, it doesn't affect your product. It will just be higher and I'll end up at exactly the same place. This could be anything. It could be mass, it could be volume. Let's just say we're using our volume over time. For our Maxwell-Boltzmann graph, if that was my original graph like that, now remember this is here particles. This is energy. So they will always give you the original activation energy. So if they give you the original activation energy, it means these particles can react. But if they give, nothing else is changing. There are not more particles. They don't have more energy. All I'm doing is I'm allowing a path of lower activation energy. So this will be the activation energy with a catalyst. So that means these particles here can also now have a successful collision. So all these particles can now overcome the activation energy, and therefore there will be a faster rate because there's more successful collisions per unit time. Okay, and that is a catalyst. So the next one we're going to do is going to be, let's just do the surface area. So again, I'm going to type that you have it there. So if we're looking at the surface area, again, we want 4 points. So what does the increase in surface area do? So remember, that's smaller particles. So now you had big lumps, now you have smaller particles. And we said there will be more exposed particles. Or you can say contact points, or just depends on how you learned this. But there are more exposed particles. If there are more exposed particles, more collisions in general can take place because more particles are exposed. If more collisions in general can take place, then more effective collisions per unit time can take place. And if there are more effective collisions per unit time, I have a faster rate. Again, there are your 4 points. Done. Now, surface area is still easy. Now we have to look at concentration. If we look at concentration, just quickly remember what concentration actually is. If you look at the formula for concentration is, let me just write it for you quickly. Concentration is moles over volume. So because it's moles over volume, this stays the same, but the volume, if my concentration increases, you need to actually look. Sometimes the moles are going to increase. So if my concentration increases, I might have more moles, but it could be because my volume is decreasing. It doesn't matter. Either way, there's going to be more moles per unit volume if my concentration goes up. So I'm going to have more particles, and that is going to be your first point. So I'm not going to write concentration because you have it there. So for my points, for concentration, you're going to say an increase in concentration means there are more particles. You can say moles if you want, per unit volume, because that is what concentration is. If there are more particles per unit volume, more collisions will take place in general. If there are more collisions, there will be more effective collisions, again, per unit time. And if there are more effective collisions per unit time, I have a faster rate. You can see those last 2 points are always going to be the same. So you just need to think about the first two. So that's my concentration. Now let's look at my pressure. I'm going through this fast because we did this in class and you all have done this in class, and it's just to refresh your memory. So the pressure of a gas, also again, if I have a gas, remember, how do I increase the pressure? So if I have a gas in a specific container and I'm now not increasing the moles, so to increase the pressure, I have to make this container smaller. So I'm going to basically squish these particles together. So instead of being there, they are now here. So I actually have decreased my volume. So I have, the particles are now moving in a smaller volume because I've increased the pressure. So an increase in pressure is almost the same as an increase in concentration because I've made the volume smaller. That's why I mentioned that earlier. So for pressure, so an increase in pressure is due to a decrease in volume. Now, if the volume decreased, it means I have more particles per unit volume. And now you'll see it looks exactly the same as the concentration one. If I have more particles per unit volume, there will be more collisions. Therefore, there will be more effective collisions per unit time. Therefore, there will be a faster rate. Okay, going fast, but you get this. And is that a temperature? I almost forgot the one that you get the most. So an increase in temperature, what does that do? Now, this one is supposed to be the easiest one, and it's the one that people get wrong most often, because an increase in temperature, you need to remember that an increase in temperature means an increase in the kinetic energy of the particles. And if you think back to the Maxwell-Boltzmann graph, increase in kinetic energy will mean there are more particles that can overcome the activation energy. So that's exactly what you're going to say. More particles have EK higher than activation energy. If there's more particles with higher energy, they move faster anyway. So there's going to be more particles that can overcome the activation energy and also more collisions. So therefore, more effective collisions per unit time. Oops. And therefore faster rate. And there we go. So all we have left to do is to see how does that affect these graphs. And the first one we actually spoke about already. But just quickly, so if we have a higher temp, if this was our graph originally, volume over time, higher temperature will have a higher curve. Higher, if I add a catalyst, it would be like that. All of these things. The only thing, if they say that you've got a decrease in temperature, then you need to know that it's slower, but I will still form the same amount of products. I'll just form it at a later stage. So it will take a longer time for me to form that product if it was a lower temperature. So just read your question. Then for Maxwell-Boltzmann, I've already shown you for the catalyst. Remember, for a catalyst, activation energy is the one that moves. So that's the effect for a catalyst. If it's more temperature, if the temperature is higher, remember the energy sits on the x-axis. So that means all these particles, have now got higher energy. So if my activation energy was there, and it stays there because I didn't change that, all I changed was I heated up the particles. So these particles that were here now have more kinetic energy. So the more particles are going to be on this side. So if more particles are on this side, then it's a faster rate. So what you will see is that the total energy under the graph must still be the same. So you will have a flatter bulb, so a bulge. So please don't think that a lower one means lower energy. A lower one with more energy after the activation energy will mean a higher energy. So this one will be the higher temperature and this one will be the lower temperature. If we increase the concentration, so that means this is my number of particles, my activation energy stays the same, my energy of my particles stay the same. So the only thing that's going to happen is that I'm going to have more particles. So these particles were added to the situation. Surface area, you can't really show yet. Or they won't ask that for a Maxwell-Boltzmann. And I think that is it.